All right, welcome back to part 2. We just want to continue on and just doing some of these practice problems. So let's look at just the next one on that sheet. We go up to 1980, no, we're not going to do 1984. We're going to go to the second page and we're going to do 1987. We're going to do this one first, then we'll come back and look at that other one. The other one's a little bit of an exception. Okay, so we have mercury 2 chloride combining with the oxalate ion and produces the chloride ion, carbon dioxide, and mercury 1 chloride. Now, again, note, mercury 1, it's unique. It is a diatomic ion. But I know that I know that chloride is -1, so that's a total of -2, so this must be +2. So each one must really just be +1. So it's Hg2Cl2, but that's mercury in the +1 state. So mercury 1, and you can kind of look up here on the chart, mercury 1 is Hg2 +2. Okay, now that's just random, I'm just throwing that out there. That's just to kind of make you, at least be exposed to that and see it. I don't hardly ever see that to where you're gonna have to know much about that. But mercury 1 is a diatomic ion. It's kind of crazy. All right. So for the reaction, the mercuric chloride and oxalic acid ion in hot aqueous solution is shown above. The reaction rate may be determined by measuring the initial rate of formation of chloride ion. Okay, so notice we're talking now. They tell you the formation of chloride ion right there. So, according to the data table shown, what is the rate law for this reaction? Well, the rate law for this reaction what's it going to be? What's my generic formula going to be? Rate's going to equal what? Times
the concentration of A.
Well, HgCl2. That's my A. Now I don't know what the power is. The coefficient's not my power. Okay, times what?
Concentration of C2O4.
C2O4, 2 minus, raised to some power y. That is not my answer to what is the rate law. I have to know what x and y are. So if I want, it doesn't matter which one you do first, but which two of the mercuric chloride, which two stay constant?
First.
1 and 2, right? So then I can kind of look at this one, 1 and 2, and see, okay, well this one is times 2. What is this one? This one's times 4, 0.5 goes to 2. Hey, now y'all, when they give you the exponents, always make sure you pay attention to what that exponent is. Okay, because if they change, then it messes up as far as trying to figure that out. All right, now, just intuitively, what do we think the power is on the oxalate, based upon the little bit that we've done already? It's going to be a 2, right? Because this is 2 times of that. But you have to show your work. You can't just say that. So to show the work, we're going to say for C2O4, the change in rate 4 is equal to the change in concentration 2 to some power y. Now on my test, on the AP test, you need to probably write that out one time, just the generic, but then you can just kind of do this. So obviously y is equal to 2. So now we need to do the same thing for the HgCl2. So what do we keep constant? What experiment should we look at here?
2 and 3.
2 and 3. But what's going to be a better direction? 2 to 3 or 3 to 2? 3 to 2, right? So that's going to be times 2. What is 3 to 2 here? Yeah, you don't have to do that on your calculator. 1 to 2, it's 2. doesn't have to be exact.
Okay.
Okay, it's experimental data. It's about twice. Okay? These exponents are always gonna be whole numbers.
Okay.
So we're gonna say 2 is equal to 2 to the x equals 1. So I say my rate law is equal to k times HgCl2 to the first, and you don't have to write the 1, times C2O4 2 minus squared. That's your answer to A, right there. Now, I just want to clarify, because I'm really kind of taking a shortcut. If I'm doing this, and I want to just start showing my work, the first thing I want to do is I want to say the change in rate, and I would say, like on this one, I would say the change in rate from 1 to 2 is equal to the change in the concentration of C2O4 2 minus to some power y. And then I would go to here, okay? I would just make sure, you know, you're kind of explaining what you're doing there, okay? Still not a tremendous amount of work, so you just do this, tell what experiments you're comparing, okay? So I would do the exact same thing on this one, change in rate between 3 to 2 is equal to, you know, the change in concentration of the HgCl2 to some power x. Then just do this. Okay? If you want to do the work complete, you need to have this for each one. All right, so that's the answer to A. B says, on the basis of the law, you know, calculate the specific rate constant. Okay? Specific rate constant. So what do I do with this?
Solve for K.
Solve for K. So, rate, again, pick one, anyone. I'm going to pick one. The rate is 0.52 times 10 to the minus fourth, and the units on it, moles per liter per minute this time, not hours. So I'm just going to shortcut that to molarity per minute is equal to K times the HgCl2, 0.0836 molar, and that's to the first power times 0.202 to the second power. So is somebody doing this?
Got 015.
Okay, and it would be 2 sig figs because of that. Okay, now what would the units be?
1 over molarity squared, or
And what time? What,
per minute.
per minute? Okay? So, Does everybody understand this part? How we're getting the exponents? You just keep one constant, change the other one. Okay? Compare the change to the change in the rate. Okay? It's always going to be your change in rate is equal to the change in the concentration to some power. Okay? Now, a couple of things. We're going to do one more and then I'm going to let you guys just practice some. But what would happen, well, there's one here. That's not it. What would happen, what would be the order if you change the concentration but nothing happens to the rate? So in other words, when I do my change in rate is equal to the change in concentration of A to some power X. If I say that the rate changed by 1, but we changed the concentration twice. You double the concentration, but nothing happened to the rate. What would X have to be?
0.
X has to be 0. Sometimes you can have what's called a zero order reaction. With respect to a particular reactant. Now, later on in the unit, we're going to talk about the reaction mechanisms, and there's going to be different steps. And we're going to have a thing called the rate determining step. That's going to be your slow step. If you have a reactant that is not involved in that rate determining step, it's a reactant, it's there as part of it, but it's not part of the rate determining step, it's not going to have any effect on the rate at all. Only the things that are in the actual rate determining step are the ones that are going to have an effect. Therefore, we can have a zero order. So you change the concentration, but nothing happens to the rate. That simply means that that particular substance is not in that rate determining step. That'll make more sense by the end of the week. Okay? So, let's go all the way to
For a question like C on 1987, would we need to make it negative, or does the disappearance?
oh no, shoot, I took that down. I wanna do that. Okay, so it was 87. Okay. So here, what is the numerical value for the initial rate of disappearance of this one? So notice we said it was the rate of formation of this. Now they want the rate of disappearance of this. Well, you got to go back to the equation. So in this equation, we measure the rate of formation of Cl minus. Okay? This was one of the reasons I picked this one, and I forgot to do the part I wanted to do. Okay? So what's my rate of disappearance of C2O4 going to be, and what did they specify?
Experiment 1.
Experiment 1. Okay? Well, what's the rate of formation? 0.52. So what's the rate of disappearance of this going to be?
Half of it, but negative.
Half of it, but negative, yes. So it's going to be 0.26 times 10 to the minus 4th moles per liter per minute, okay? But you don't really have to put the negative because what's the question asked?
The disappearance.
What's the rate of disappearance? So the rate of disappearance is 0.26. Because the question specifically said 0.26, now it would not be wrong to put the negative, but the word disappearance tells me, you know, which direction I'm going. So you'd win with or without the negative sign. But that's how they introduce relative rate law. They give you the formation, that they give you the rate based upon one thing, then they ask you the rate of another. Well, once you do that, I mean, we really didn't have to do part A or B in order to be able to do C. You can do C just by looking at it. That's the relative rate law thing. And what's D as?
Calculate the initial oxalate ion concentration for experiment 4.
Okay, so in other words, they're asking for this. Well, we would know, you know the rate, you know the value of K, we've gone through and calculated K, which we don't need to necessarily go through and do, okay? Once you know K, you know the rate, you know everything except this one, you just plug in and solve for this one. Right? So once we get the exponents, we solve for K, that's not too hard, just remembering the units. Then you can solve for anything. And you always just pay attention to the relative rate law. And whenever they're saying what's the rate of this compared to one, always come back and look, well, how did they measure the rate in terms of what? And then it's just stoichiometry on that part. All right, I want you guys, we'll practice one more. Did I just say which one I wanted to do? There's so many choices. Okay, let's look at 94. Just do A and B on 94 for now. This was actually on first semester. All right. So who wants to walk me through this one?
Not it.
All right. Let's see. Back row gets to do it. So Chris, go.
So the rate would be just like K times N to the X of H to the Y.
Okay. So we're going to start with the rate. Is equal to K times NO to the X times H2 to the Y.
And then the rate of NO you find where H2 is constant, so that would be 3 to 4.
3 to 4.
Yeah.
So here it's going to be times,
2
and what happens to the rate?
times 4.
Times 4. Now we just already just intuitively know then the power, the exponent on NO is going to be 2. But we have to show our work. So,
the
go ahead.
rate equals 2 to the X. The rate equals 2 to the X.
First thing I'm going to say is rate from 3 to 4, change in rate from 3 to 4 is equal to the change in concentration of NO raised to some power X. So then I'm going to say, what, rate changed by how much? 4 is equal to 2 to the X, X equals 2. To show work, that's what you really, I really want to kind of see. And yeah, I need to see this, so it kind of explains what's going on. All right? So then we do the same thing, right? So the change in rate from, what do we do for the H2?
We're going to go from 1 to 2.
1 to 2, right? That's times 2, and this is times 2. So that tells me that it's going to be, what's the exponent going to be? 1. Whenever the rate and concentration and rate change the same, it's 1 to 1. But we're going to say 1 to 2 is equal to the change in the concentration of H2 to some power Y. So 2 is equal to 2 to the Y. Y obviously is equal to 1. Okay? So it doesn't take that much extra, but that explains what you're doing. Okay? So on an AP test, this is your work. You can't just put the values, you have to show some way of how you got it. We read, when we grade, we read this stuff. Okay? So that I just kind of look to see the overall thought process as best we can. Okay? So the rate then is going to equal K times NO squared times H2. So what's the order with respect to NO? 2. What's the order with respect to H2? What's the overall order of the reaction? 3. Okay? Order is just the exponent. overall order sum of the exponents. All right, so that's A. All of this is the answer to A. So then B is rate constant, right? Calculate the constant with units. All right, I'm gonna do it up here just so it's easier to see. So which experiment did you pick? 1. So the rate, 1.8 times 10 to the minus 4th. And I always now just come and check, what's my time on that one? Because time is the unit that, you don't just assume seconds, minutes, or you just gotta look. So it's gonna be molarity per minute is equal to K times my NO concentration, 0.0060 squared, times 0.0010 to the first. Okay, we know that this is molarity and molarity, so it's molarity squared. So what number did we get?
I got 5,000.
5,000. Okay, now that would be 2 sig figs. So we could, the best way to do that is say 5.0 times 10 to the third. You could put a bar over the 0 next to the 5, is 5,000 as well. I'm going to 2 sig figs. Okay, but what are the units going to be?
1 over m squared, molarity squared times units.
Times minutes. That all equals K. Still algebra. Are we all comfortable with that? Now, they don't ask it. Okay? For experiment 2, what is that third, what does that say? Calculate the concentration, we'll come back to that one. But if I'm given this, notice that it's saying the rate of formation of N2. What would if I said for experiment 2, what would be the rate of disappearance of NO?
Double.
Okay, it's gonna be double, right? Because it's a 2 to 1. For every one of these that gets formed, 2 of these are gonna disappear. So it'd be 7.2 times 10 to the minus 4. Relative rate law. Then you could fill in what's the rate at any given concentrations. You just plug in the concentrations. You know K now. You find the rate. And once you have the equation with everything, K and the exponents, then you can be given other variables. Just solve for the one that you don't have. Very easy. So far, so good? Not too bad. All right. Let's put one little wrinkle to it. You guys are all good in math, so the wrinkle's not going to be that big of a deal. We're going to go back to 1991. If I can find it. I have it here. 1991. There it is. First page. So here's my data. It looks, write the rate law, calculate the variable constant, it looks like it's just like all the rest of them. But does anybody see the problem? The challenge?
The change in, yeah.
What doesn't
Oh,
happen?
never mind. Constant.
There's no constant, there's no 2 that are the same. Okay? So we would kind of like have 2 variables in our equation. So we have to eliminate one of the variables, which means that I've got to figure out what this exponent is first, because there is a time when this stays constant. Now I can pick 1 to 4, 1 to 2, either way, but let's do this right here. Okay? Well, pardon me. We want to compare these two. Keep this constant. What happens here? times 4. What happens here? Times 4, right? So I do the exact same thing. Do the exact same thing, so my change in rate from experiment 1 to 2 is equal to the change in the concentration of F2 to some power, I'm going to make it what? Now, my rate changes by 4, my concentration changed by 4 to the Y, so Y equals 1, right? So now I know that value. So now it's no longer a variable. So now when I go and I want to figure out how does the change in concentration here, now I can compare 1 to 3. And I can compare 1 to 3 here. And I compare 1 to 3 here. So I can now say that my change in rate from 1 to 3 is equal to the change in concentration of ClO2 to some power x times the change in concentration of F2, but now we know that that's to the first. So it's no longer a variable. Right? So now I can say the rate changed by 4. I changed the Cl2 by 2 to some power x, and I changed the concentration of fluorine by 2, but I know that's to the first. Because this is times 2, this is times 2, this is times 4. Did everybody follow what's going on? You find the one that doesn't change first by using the one that does stay constant. That takes it out, but you just have to include it when you do the next one, you just have to include it, but it's no longer a variable because we know what the exponent is. So, obviously, what must be x?
1.
Okay, so, I mean, if you want to do the math, divide by 2, so 2 is equal to 2 to the x. So x equals 1 again. Once you get to there, everything else is the same.
Could you have chosen any 2 experiments for the second part?
Yep. But I like the double factor, it just makes it easier. I always try to figure out the easiest multiplication. All right. So, I have a problem in my head. I just cannot remember where it is. Maybe it's in your book. If we look at number 33. This is number 33 in your textbook. It is page 619. You're just cruising right along through this book. Okay? Because we've done everything up to that point. All right, so again, let's just generically go through this. Let's not even worry about work. Let's just try to figure out what the exponents are. So I know that I can keep this one constant, right? So what's happening to here? Times 2. What's happening to this? Times 2. So what do I know my exponent, my power is here?
1.
It's a 1. Okay? So now, I keep these two, so now I'm gonna compare here, this is times 2, and that's times 2, right? So what's my I minus? 1. Alright? I was kinda hoping that it wasn't gonna be that, but. And then calculate the rate constant of proper units, calculate the rate, so once we have that, then here, these are just classic problems. I'm trying to find one that's 0 order. There's one with bromine in it somewhere. Okay? We got all kinds of data on this one. So, let's again, generically, let's do this. Which ones, what do you want, how would we do this?
Compare 1 and 2 for.
Compare 1 and 2, really 1 to 2. So that's times, what's this? Times 2. So I know that that's a 1. What else?
3, 4, or 4, 3.
4 to 3? Is that gonna be my best? I would do 5 to 4, because that's the times what? Yeah, just times 2, just make it nice and easy, find the ones that the easiest. Now, it works with fractions, but it makes the exponent a little bit more challenging. I always like to try to find the one that's a nice whole number, okay? What happens to this? Times 2, right? So what do I know my power is here? 1. I keep, these are all just so easy, okay? Oh, that was that one. What about 34? Oh, there we go. Okay? So this is times 3, right? Now this one is not intuitively obvious. So how do I figure out what it's multiplied by? How can I just, this one you might want to use a calculator. What do I do? If it's a times, how do you go the reverse of times? Divide. Okay? So to always divide the biggest one by the smallest one. Figure out how many times that goes into that one. That'll be your times.
It's 8, yeah, 8.98.
So 9, right? So if you times 3 times 9, what do I know my power is on CLO2? 2, because 3 squared is equal to 9. Alright? So now, we need to compare here to here. This is times 3 again. What's this one? Times 3. Now, if this one had said 0.00276 instead of that, what would the order have been? Not 1. What, Ben? 0. When you change the concentration, but there's no change in the rate, that's when it's 0 order. Okay? My brain is getting old. I have a 0 order problem that I can't find it. I know where it is in my head, but I can't find it in all the paperwork. I'll find it during the break and I'll show it tomorrow. On the video, you guys get to watch. All right. Let's see if we can do one more to where it doesn't remain constant. 1984. We'll let you do this. Got the rest of the period, go through this problem. And we'll go over this first thing tomorrow. Now, you do not have to do, you just really need to do part A and part B. Part A and part B. We'll learn how to do D later, we're never gonna learn how to do C.